Hello dear learners, in this lecture we will continue our mathematical treatment of deriving the Chapman's theory or Chapman's production layer. In the last lecture we have obtained this expression which is 1 by n dn over ds is equals to cos chi divided by capital H. I already explained what is the meaning of this expression. This expression simply tells the rate at which normalized change of number density with respect to the oblique distance is equals to cos chi divided by capital H. How is this different? Because n is equals to n naught exponential minus h by h. So, dn by dh is n naught exponential minus h by h into minus 1 by capital H, or 1 by n dn by dh if you are asked will be 1 by minus 1 by h scale height. This is how it is different. So, an additional factor of cos chi is appearing, which is actually like I said in the last class, is just a scaling factor which is converting variations with respect to h in terms of variation that we know with respect to small h. This is one relation that we have defined, and we have this expression which is 1 by n dn by ds at maximum plus 1 by I di by ds at max is equals to 0. And in the last lecture itself we have defined this ln of I by I infinity is equals to minus sigma n of chi. Now, if you remember that condition, that to what distance will the radiation penetrate? The radiation will penetrate to a distance where sigma n is simply equal to 1. So, you use this and assume that intensity has been absorbed completely. So, we can write ln I by I infinity is equals to minus 1, or we can write I infinity by I is equals to E, or I is equals to I infinity by E. Okay. So, we have these three expressions from the last lecture, or let us say we call it as 1, 2, 3. So, radiation by the time it reaches the peak production height decays to 1 by e-th of its original intensity. Okay. Substitute all these things into equation number 2, we can get cos chi divided by capital H plus 1 by I di by ds. Di by ds is minus sigma n I at m is equals to 0, right. So, where did I get this? I got this from di by ds is equals to minus sigma n I. Remember, di by ds proportional to n and proportional to intensity. Removing the proportionality, we introduced sigma, and since the intensity is decreasing in its magnitude as a function of s, we put a minus. That is what we have directly substituted into this expression, right. Now, we can rewrite this expression in simple terms, which is cos chi divided by capital H minus sigma n m is equals to 0, I getting cancelled, that is it, okay. Or cos chi minus sigma n m capital H is equals to 0. What is this? This is a condition. What is the meaning of this condition? At the peak production height, this condition becomes valid. So, you take a certain angle, that angle cos chi minus the maximum number of atoms or molecules at the peak production height, the scale height and sigma, they will all obey this equality. We can rewrite this expression as, let us say we write cos chi minus sigma nm capital H is equal to 0, or 1 minus sigma nm capital H secant chi is equal to 0, right, or sigma nm H secant chi is equals to 1. So, scale height, I also define the scale height with a subscript m, just to be simple. So, sigma nm hm secant chi is equal to 1. Okay. So, what happens at h is equals to hm at a height which is equal to the peak production height? We know that n sigma is equals to 1, and at the same height we also know that I is initial intensity divided by E, right. And so, we can write the production Q as Q is equals to Qm, and we are defining Q to be Qm, and Qm is equals to C sigma Nm Im, but we know sigma Nm Hm secant chi is equals to 1. So, we can write sigma Nm is equals to 1 by Hm secant chi. What am I doing? This condition is what we got by assuming Q reaches peak at H is equals to Hm, fine. So, dq by ds becomes 0. When Q reaches peak, I am going to call that Q as Qm. Of course, its change will become 0. Right now, I am not bothered about that. Q is equals to Qm. So, if it is Qm, so this is from the earlier expression. This is, remember, the unit change of intensity or unit decay of intensity produces C number of electrons. So, total decay will produce C times that number. That is the same expression, you can go back and see that. So, this is what I have used from the earlier expression. Let us say we call it as equation number in this class. Have we given any numbers? Okay. This is equation number 4 and this is equation number, let us say, 5. But we have an expression for some of the variables which appear in this expression. We call it as 6. Okay. But some of the variables in equation number 6 seems to obey this equation, which is equation number 5. From that, I deduce sigma Nm is equals to 1 by capital Hm secant chi. Obviously, substitute this into equation number 6 and I write Qm is equals to C sigma 1 by, yeah, I might as well put sigma here, Nm, C sigma 1 by sigma Hm, both I secant chi times Im. Okay. So, Qm is equals to sigma gets cancelled, C Im divided by Hm times cos chi. 1 by secant chi is cos chi. Let us write it again, QM is equals to CIM by capital HM times cos chi. But we know IM is I infinity by E. So, we can write QM is equals to C I infinity divided by E HM times cos chi. Okay. So, QM, what is QM? QM is the peak production rate or production rate at the peak. So, this is the ionosphere basically. This is number density which is per meter cube and this is kilometer, right. So, maybe we can just go back and see what we have done. Just we have defined how intensity changes with respect to height or intensity with respect to height with respect to small s, okay, and how number density changes with respect to small s, and the production seems to be dependent on intensity and number density. So, Q reaches QM, that is when rate of change of Q becomes 0. Using this we have got two terms, both the terms independently we have evaluated and added, and subsequently we got this. Okay. Right. So, are we complete yet? No, we have not yet reached the final result. Okay. Now, QM is the peak number of electrons produced at one altitude, not every altitude. Okay. Now, these electrons which are produced are also lost, is not it? Some of them are lost. So, at the peak, despite having the loss processes, the electron density is maximum. Okay. So, if the electrons are lost at a rate of alpha E square, and if the photochemical equilibrium is reached, then you would obviously expect the total production rate is equal to the total loss rate. Okay. So, which means QM has to be equal to alpha times EM square. What is EM? EM is the electron density of course, but at the maximum value. So, we can equate alpha times EM square to be equal to C I infinity divided by E HM cos chi. So, the peak electron density EM is equals to C I infinity divided by E HM alpha raised to the power of half times cos chi Okay. Now, based on few simple assumptions, we now have an expression using which you can calculate the peak electron density. Of course, you can calculate the peak electron density as a function of solar zenith angle, recombination coefficient, an exponential factor E, HM, the scale height, and initial intensity, right. So, these results are not applicable directly, rather these results are applicable when we have considered a single absorbing gas. That means, all the species which are contained are all the same, there are no changes in the absorption cross section of these gases, okay. And they are also distributed with the same scale height, okay. That means, capital H. So, single absorption gas with any kind of distribution with respect to height, it could be anything, right. Now, what does it mean? It means a lot. Before we try to understand what lies ahead, here we have not defined how the gas densities are distributed with respect to height, is not it? So, they can be distributed in any way. Okay. So, absorbing gas with any kind of distribution with respect to the height. Okay. Now, let us say we have the particles or the atoms and molecules which are vertically distributed in an exponential way. We will keep this result, we will use it in the subsequent discussions. Let us say we number it 6, we call it as 7, and this is equation number 8. Okay. Now, let us say we have neutral species which have a distribution something like this: n is equals to n naught exponential minus h divided by capital H. Now, what the earlier expression that we have, the equality that we had was rather simple, which is sigma Nm Hm secant chi is equals to 1. Okay. Now, we substitute this into this expression: sigma n naught exponential minus h by h okay, obviously. Okay. So, we can write it as, from this we can write exponential h m by capital H is sigma n naught h secant chi. Okay. Just some simple algebra, so we call it as equation number A. Now, intensity depends on the height. So, di by ds is equals to minus sigma ni, we already know that. Now, multiply this expression with C, you get Q, the production rate, right. Now, intensity variation also with respect to the vertical distance di by ds can now be written as di by dh times dh by ds, which is also equal to minus sigma ni. From what we know from the earlier discussions, di by this is equals to di by dh times minus cos chi is equals to minus sigma ni. So, di by dh is equals to sigma ni secant chi, or di by dh is equals to sigma n naught exponential minus h by h times secant chi. Now, I can write di by I is equals to n naught sigma exponential minus h by h secant chi ln okay. Just integrating this, we got that. So, intensity I is equals to I infinity exponential minus sigma n naught capital H secant chi exponential minus h by h. What I have done is very simple. I have just applied the chain rule and I have converted variation of intensity with respect to oblique distance into variation of intensity with respect to the vertical distance. You see, that is what it is. You just look at the mathematics once again, you will understand what has been done. What has changed is we know how the intensity is changing with respect to the height. So, the additional factor of course, now is the scaling factor, right. Now, this is the intensity, right. Now, we know that the rate of production Q is equals to C sigma n I. This is something that we have been using since the beginning of the Chapman layer. Let us name the equations. This is equation A, this is important. That is what I said, right. If you multiply with C, what you get is Q on the left hand side, production rate. Okay. So, this is an important equation. We call this as 8, and we can call it as 9 and this as 10. Okay. So, we will continue this discussion in the next lecture.